I am going to be going over chapter 14. I don't have the camera on. To be honest, I just did not feel like putting makeup on today and looking nice. So, this is going to be our last chapter for, well, it's close to the last chapter, depending on what school you're at. It might or might not be your last chapter, but can you believe we are at the end of the semester? That went pretty fast, right? So this week we're going to be looking at internal processes, right? Like, what does that mean? We're looking at these supreme builders of terrain. What gives us our faults, our volcanic activity, crustal movements, folding, faulting, all these things, these are constructive, uplifting building processes. They tend to increase the relief of the land, change the surface of the land, and they're internal processes because they happen within the earth, right? So we're looking at this movement from the idea that our earth, our continents are fixed to the idea of plate tectonics. So we're going to look at that shift within science. Okay, so when we look at the positions of our continents, right, like Africa, Australia, Asia, Eurasia, South America, right, our continents, the shapes and positions might seem fixed or permanent. But geologically speaking, continents are moving. They are mobile. Continents have moved, collided, they've merged, and these changes continue today. So the current placement of our ocean basins and continents is not permanent. Obviously, in our lifetime, we're not going to see that movement, right? It's very, very slow. So it doesn't happen in a human's lifetime, which is what, 80, 90 years, which is very short. Geologically speaking, we're looking at thousands, millions of years, if you will. And some people will say, hey, that's, not how long our earth has been around, but that's another whole nother discussion. So by the 20th century, most earth scientists thought that the crust was permanent. So we're going to talk a little bit about that shift within the scientific world, if you will. And that kind of changed a lot of things. So until recently, the idea was unaccepted in the scientific community, right? Though it was not widely accepted, the idea that the continents have changed position over time or that there was a supercontinent, it's been around for a while. So back in the day, Alfred Wegener, he came up with this idea that there was a supercontinent named Pangaea, which existed about 225 million years ago, and that it eventually broke apart into the larger sections that we know today, that we see today in our global maps, right? Unfortunately, there was no scientific proof that this was true. So Wegener said that, yeah, there's evidence supporting his theory, right? But he didn't have the actual proof, if you will, to support the idea of continental drift. Okay, so Alfred Wegener, he really collected a large amount of evidence to support this theory, this hypothesis. So here's another picture of Pangaea, and down here we have Wegener's Pangaea. Up here is like more of a modern construction of probably what it looked like 225 or so million years ago. So his evidence for continental drift, it was just a few things he collected, and he proposed this hypothesis. Hey, you know what? South America and Africa, they have the same fossils in around the same area where they look like they fit. Are you following this? So there was like rocks that were found on both sides of the Atlantic Ocean that must have once been together or been part of one landscape. So he found this evidence. He found that South America and Africa fit together like a puzzle. He also found the same rocks. The fossils of some dinosaurs and other reptile species, they were found on both sides of the Atlantic Ocean. Fossilized plants were found in similar aged rocks in South America, South Africa. So for this reason, during that movement of Pangea, Madagascar broke off modern-day Africa and was left to itself. So during that time, that is why Madagascar is one of the most unique and biodiverse places on Earth. So if you don't know, Madagascar is kind of like, it's this area here, this little island on its own. You know, and if you've seen, I haven't seen the Madagascar movie, I'm a little too old for that, but a lot of their animals are very unique in comparison with other animals. Lots of biodiversity. I mean, there's like 1,400 different types of chameleons. So the species were really left to evolve on their own on this island. Some of the most unique species on Earth are found here and only here. So this would be Madagascar over here. And here's just another picture. These pictures from the book, they give me these resources for teachers. Some of them are kind of like this picture, right? You guys would be fine if you didn't see this. It's kind of like, okay, weird. Let's look at the theory of plate tectonics or tectonic plates, right? So the evidence. By the 1950s, now we had like more of these technological advances. Scientists had now way past the time of Alfred Wegener, just to be clear. Alfred Wegener, all he really did was collect fossils, right? And he said, you know what, all these countries and continents, they fit together like a glove, but there was no way for him to prove that these continents were moving. He had kind of this evidence, right? He had this quote unquote crazy theory. Not until the 1950s did we really find the proof for the movement of these continents. Are you guys following this? So by the 1950s, scientists had accumulated a really large amount of evidence about the ocean floor, the underlying crust, the layers of the Earth, how our plates, how our Earth, the crust of the Earth is divided into different plates, because we had the technology to go into deeper depths in the ocean. Because a lot of our ocean life hasn't been was only discovered by in the 1950s, and I covered this in chapter 9. Remember I said that by the 1950s we had that technology to go deeper, to find more things going on in the ocean. Before that, we thought the ocean was this like large, empty abyss in terms of like physical features, right? Not until then that we discovered that there was chains of undersea volcanoes, oceanic trenches, underwater volcanoes, I said that, ocean floor topography. We discovered that there was a lot of things going on in the depths of the ocean that we really didn't imagine. And 1950s to us, even to me, sounds like so long ago, right? But geologically speaking, it's a pretty recent discovery, and this discovery is not just like, oh wow, this is pretty much something that rocked the scientific and geological world. It was a huge discovery. By the 1960s, there was a world network of seismographs that was able to pinpoint the location of every important earthquake in the world. So instead of it being this abyssal plain, we found that the ocean was full of undersea volcanoes and deep oceanic trenches. And so what now, 10 years later, we started to map those earthquakes. And when the locations of these earthquakes were mapped, it showed that they were not random, but the earthquakes occurred in certain specific bands coinciding with the pattern of these mid-ocean ridges. So I'm going to get into that in a little bit. So you have kind of like these mid-ocean ridges all along the world, the globe, right? So like if you were to take the globe and you'd run your hands across it, it's kind of like these baseball seams that you can kind of feel. And these are known as mid-ocean ridges, or you can call it the Mid-Atlantic Ridge, the East Pacific Rise. There's different names for them, but technically this is where you have the seafloor that is spreading away from each other. Now, as it spreads, you have this oceanic floor plate, you have this plate here, and they're moving away from each other. As it moves away from the center, from a different layer of the earth, you have magma that is rising, and it comes out and it forms these really high mountains. So if this scribble scrabble here looks crazy to you, I have these pictures on the next slide, don't worry, but this is how these underwater volcanoes and mountain chains, if you will, form. You have these two oceanic plates. This is an oceanic plate. They're moving away from each other. Then you have this magma lava that comes up and forms these really, really high mountain chains. So this is the theory of sea floor spreading. The theory states that these mid-ocean ridges are formed by currents of magma rising up from the mantle. These volcanic eruptions create this new ocean floor that spreads away laterally from the ridge. It's just what I explained. This is just the definition from the book that I just repeated. So mid-ocean ridges, they are going to contain the Earth's newest crust. So if you were to follow this pattern of thinking, you would say, okay, well, the Earth is supposed to be getting bigger in size, right? If it's new crust at these ocean ridges, then you would think that, hey, the Earth is getting larger and larger in size. However, as these oceanic plates move away, they come in contact with, say, a continental plate. And so you have these other zones, either convergent zones or divergent zones, where plates are coming in contact with each other. And this is where you have most of your geologic activity, all these forces creating volcanoes, mountain ridges, trenches, all this stuff, earthquakes, tsunamis, all this stuff going on. So here we have all these little red dots are the locations of pinpointed earthquakes. So when they did have the mapped locations of earthquakes, it wasn't just it wasn't just sporadic, right? When they pulled it up, they said, hey, you know what? All these red areas have something to do with where we have these mid-ocean ridges and these different plates coming in contact with each other. So then you had more of this proof for seafloor spreading, for the continental drift, if you will. So when these locations of earthquakes were mapped, it showed that they weren't random, but earthquakes occur in bands coinciding with the pattern of mid-ocean ridges. All right, so let's look at seafloor spreading. I did show you this terrible drawing in the past two slides of what I was talking about. And this is a better picture, right? So you have these two oceanic plates moving away from each other, right? And as they move away from each other, you kind of have this magma coming up to the surface and allowing and kind of pushing those plates away from each other. Okay, so this is seafloor spreading. You have mid-ocean ridges, you have volcanic eruptions that create new ocean floor, and these are the new ocean floor is spreading away from the ridges, right? So in theory, this ocean floor here, would it be younger or older than this ocean floor here? And this is where you guys would all say, this ocean floor is younger, right? If we were in the classroom, yeah, this is your younger ocean floor, right? Because this is all brand new earth, if you will. Okay, so this would be older. And that's another way they were able to prove that. They took these core holes that they drilled into the ocean floor and they tested them. And you can see that these sediments are much younger than these sediments over here. Okay, so this indicates that sediments furthest away from the ridges are oldest, right? Any sediment near the ridge is young. So we're looking at evidence and proof to this theory. Verification of seafloor spreading, it's just what I said in the last slide. You had these core holes drilled into the ocean floor by a research ship in the late 1960s to be exact. The sediments they collected from the ridges were, furthest from the ridges were oldest and closest to the ridges were thin and young. So this is how we prove that, Wegener was correct, that seafloor spreading, or actually Pangea, his theory was correct, right? That the continents were moving. He just didn't have a way of proving that, not until way past his time were we able to prove that. So that is the verification of seafloor spreading, or plate tectonics, or continental drift, if you will. So what happens? How do we not get bigger in size, right? If you were to follow that idea, you would say, okay, well, the Earth is getting bigger and bigger. But something is happening where that new Earth is being recycled back, right? So obviously this happens over many, many, many years. But I want you to look at this picture here. And if you can, take some time and draw it out yourself. Like, I would encourage you, if we were in a lecture, to draw your seafloor spreading like this with the arrows, which way it's going. This is oceanic floor, and then when it comes in contact with like continental crust, right? So there's different types of crust. Maybe I didn't explain that. You have oceanic crust and you have continental crust, and that's just what it sounds like, right? Continental is going to be on your continents. That crust is continental. It's older, it's more buoyant, it is older and more buoyant, right? And then you have oceanic crust, which is newer, it's denser, it's heavier. So keep that in mind, okay? Oceanic versus continental crust. And you can say, you have oceanic plates and continental plates, okay? So here we have seafloor spreading going on right here, okay? Now, you have your rising magma that comes up, right? And it pushes away that seafloor. It's opening up. You have these mid-ocean ridges. Cool, perfect, right? You have that lithosphere moving away, pushing away. Now, it's going to come in contact eventually with another plate. Now, here you have a continental plate. Anytime you have an oceanic plate come in contact with a continental plate, you will always have this oceanic trench because this plate will subduct. It will always go underneath continental crust. Always, always, always. Why is that? Because oceanic crust is denser, it's heavier. It will always subduct. Continental crust is older, buoyant. Okay, so this is going to subduct. It's going to create a trench there, okay? And at the bottom of the ocean floor, you have a bunch of dead organic material. And as that is pulled underneath, now all that carbon or that CO2 needs to escape. So now it comes up and then it escapes via volcanic eruptions, okay? So anytime you have a continental and oceanic convergent zone, you will always have a trench and you will always have volcanoes along that trench parallel to it. So this would be oceanic continental convergent zone, okay? Mechanism for plate tectonics. How does this happen? Well, you have convection within the Earth's mantle, and those plates are slowly moving over the asthenosphere. So you have like this sluggish thermal convection system that appears to be happening within the planet. This brings deep-seated, hot, lower density rock to the surface. The plates are pushed away from mid-ocean ridges, but much of that motion is a result of the plates being pulled away by the subduction here. So yes, you have you know, hot molten rock coming to the surface, pushing away those oceanic plates. But a lot of it too is that subduction, which is pulling it. Okay, so it's not just the pushing, it's also the pulling, that subduction. And so we have our different plates. So you can have continental, oceanic plates moving atop of that layer, right? You have the crust moving on top of the asthenosphere. So before you watched this, you did have a couple videos about the structure of the Earth. Okay, so hopefully you guys are understanding what I mean by the asthenosphere, the lithosphere, the crust, right? Those are the top layers of Earth. Then you have the mantle, correct? So now let's look at plate boundaries. I did cover a little bit about convergent zones and divergent zones. So we went over mid-ocean ridges, and then where you have oceanic coming in contact with continental. But now we're going to specifically go through these as these plate boundaries. Okay, so remember, plates are relatively cold and rigid. Therefore, they are deformed significantly at the edges and only where one plate collides or interacts with another. Most of the action in plate tectonics will happen along plate boundaries. So there are three different types of plate boundaries. You have divergent, convergent, and transform boundaries. This is where plates are coming in contact with each other. Okay, they either meet, move away from each other, or slide across or side to side, parallel to each other, if you will. Okay, so I'm going to go through this, and yeah, I'm going to go through it. All right. So here are those different boundaries. You have convergent down here. You can have oceanic convergence, oceanic continental convergence. You can also have continental, a divergent boundary, and a transform boundary. Okay, these are all the different boundary zones. Remember, there's three. And the convergent type, you have three different types under that. Okay, so here are our plates. So when I was showing you the oceanic divergent areas, before that, there was another slide with this picture that I kind of clicked over way too quickly. So our planet, our crust, our lithosphere, if you will, is broken up into different plates, right? You have these large plates, the Pacific plate, the Eurasian plate, Pacific plate, North American plate, right? Nazca plate, if you will, like you have a bunch of different plates, and they are all coming in contact with each other. So they're either converging, subducting, converging. They're either diverging, moving away from each other in those mid-ocean ridges. Obviously, all these are divergent plate boundaries. How do I know that? Well, the map shows it here that this red line is divergent, but I know that in the ocean, plates are moving away from each other, especially in these divergent ridges, right? And then where you have this little, like, what do you call that? I don't know what you would call that. Well, this means that this plate is subducting underneath this plate, right? So let's see. This plate is subducting underneath this plate, right? So we're going to go through these different boundary zones. So divergent, I did a pretty good job at explaining your seafloor spreading, I think, and that's a divergent boundary. So you have magma welling up in the opening between plates, creating or at mid-ocean ridges, right? And these plates are moving away from each other. They're diverging. You also see this on a continental area. So it's like seafloor spreading, however, on a continent. And we see this in one place, and it is the Great East African Rift Valley. So it's kind of like what's happening here, but however, it's over a continent. So let's look at that. I will have a video about this continental Rift Valley. What's going on here is you have the continental rift zone. You have kind of this continent, and you have kind of this pressure coming up, and the crust is opening. It's like pulling away. So one day in the far, far future, all this ocean is going to come in here, and they've already named this ocean because this little ear of Africa will rip off and drift into the sea. Now it sounds dramatic, right? It's not going to happen in one punch. It's going to take time. But they've already named this ocean the Afar Ocean. And this is the continental rift valley. So this is what's happening here. You have continental crust. You have this magma coming up and blistering open that crust. And you have to understand that our crust is very, very thick. Continental crust is way thicker than oceanic crust. Okay, so there's no way like this is going to open and all this magma is going to like come out and, you know, like some apocalyptic occurrence. No, that's not going to happen. It's so thick and it's just going to open up and then the ocean will come in and fill it in. You guys following that? It's kind of hard to understand. I have a really good video that I will link onto your module about this continental rift valley, okay? Now let's go into your convergence zone. So these are called constructive boundaries because they create mountain ranges, volcanoes, oceanic trenches, and there's three types. So we have oceanic continental convergence, oceanic convergence, and continental convergence. Okay, all of these are called convergent boundaries. Okay. So you have oceanic, continental, oceanic, continental. We know a little bit about your oceanic continental convergence because I did go over that, right? So you have oceanic crust subducting underneath continental crust. You have a trench here. You always have a chain of volcanoes here. Always. That's what's going to be happening. Now, in an oceanic convergence, you do still have subduction. You still have a trench here. And you still have a volcanic range here, but instead of being like a mountain range, it's going to be an island arc. We're going to call them little islands because it's under the ocean. It's going to create these, right? It's still volcanoes, but it's more of an island. So we call these an island arc. And then continental, no crust subducts. You just have this complete, and how do I say, you just have this rising of crust, right? So continental, this is where a convergent boundary between two continental plates. There is no subduction here, and I'm talking about this here, right? This is because continental crust is too buoyant to subduct. Instead, you have these huge mountain ranges that are built up. For example, the Alps or the Himalayas. Most dramatic present-day example of continental collision is the formation of the Himalayas. So they are always getting higher and higher because that subcontinent of India is moving into the plate of the Eurasian plate, and it's just creating those Himalayas to get higher and higher. So, little breakdown of each convergence zone. I would stop it here, pause it, take notes, write this down. This is oceanic continental convergence. Hopefully you are starting to understand it by now. This is the third time I explain this. Okay, so you have this oceanic crust coming in contact with this continental crust, right? Oceanic crust will always subduct and create a trench here, oceanic trench, right? That means it's really, really deep, okay? Then along the trench on the continent, you have a mountain range and volcanoes within that mountain range, right? Because all this stuff that is dragged underneath or dragged, it has to escape somehow as CO2, and it does so through volcanic eruptions, okay? So oceanic always underrides continental. This is a subduction zone. You have mountain ranges like the Andes or the Cascade Mountains, the Andes you have in South America, where that Pacific plate is going underneath the, I think it's the South South American plate. I might be wrong. And then you have a oceanic trench parallel to that. And this would be a continental volcanic arc. That's what we would call this here. Continental volcanic arc. That's just the name of this entire mountain chain, if you will. This is a continental volcanic arc here. Okay, now let's look at oceanic convergence. The same thing, I think, is happening. However, it's underwater, right? And this is an oceanic plate. It's oceanic crust. You have oceanic crust, subducts. Then you have this same thing. CO2 needs to escape. But instead of it being like a mountain range, this, we call it an island arc. Okay, you see this a lot in close to Japan, right? You always have all these volcanic eruptions off the coast. It's almost like new little islands are being born all the time, okay? This leads to shallow and deep earthquakes within this trench. This is where you have a lot of tsunami activity, and we will talk about tsunamis. I think it's the next slide or in a couple more slides, and how that happens, because they have to do with this oceanic convergence. Yes, so let's look at the tsunami of 2004, in December of 2004. So what happened here is you have this Indo-Australian plate subducts underneath this Eurasian plate, this whole thing over here. Hopefully you guys can see what I'm drawing. So this Indo-Australian plate is going underneath this plate. And so it created this 9.1 magnitude earthquake. And I will link a video because it's very impressive to watch this National Geographic like a mini documentary. But you know, a lot of the death that happened, they think could have been prevented if people sought higher ground once that earthquake hit, because there's a lot of video of people just being on the beach and like watching that drawback. So what you have is you have this oceanic plate, and you kind of have like this thrust slip earthquake, and it's a huge displacement of water. It's not just like a little rumbling, it's this huge like thrust, if you will, of those two plates, and it displaces a lot of water. So a lot of that water comes back, draws back to fill in that void, and the beach is left empty. And so now you have, it comes back, right? And so that would be your tsunami. So this is a very, not recent, but I would say in our lifetime, a tsunami we think about, and also the tsunami in Japan that happened recently. Maybe not recently, but in our lifetime as well. This is the one I choose to kind of highlight. Okay, continental convergence boundary. Continental crust is too buoyant to subduct, and this gives you these very large mountain ranges like the Alps or the Himalayas are two examples of a continental convergence zone. So here is India 71 million years ago, way down here, and it's continuing to go into that Eurasian plate, and it will just continue to get smaller, if you will, and these Himalayas will get higher and higher. So this is what's happening. You have that subducting oceanic plate, and then you have this continental crust in the middle of that plate going straight into this continental crust, and then this is modern day over here. Pretty interesting, right? I love this stuff. This stuff to me is so interesting and exciting. Transform boundaries. This is where you have two plates slipping past one another. They do not create new crust nor destroy old crust, A great example is the fault in California, the San Andreas Fault. I don't know if you guys have ever been out there, but I know high schools used to take the kids out there for field trips, and like you can literally stand on the Pacific Plate and the North American Plate, and if you're a super science nerd, you get really excited and take pictures, and one foot is on one plate and one foot is on the other. But this boundary, you have two plates sliding across each other. They're not creating new crust or destroying old crust. Transform faults are associated, however, with a great deal of seismic activity. Most commonly, they produce shallow earthquakes. The most famous fault system in the United States is the San Andreas Fault in California. So here is the San Andreas Fault. So you see all these faults here in California. This is why we have so many earthquakes, right? A lot of geologic activity going on here. I get really freaked out thinking about earthquakes because I'm old enough to remember a lot of earthquakes. So 1987 was a Whittier earthquake. I don't remember that, but there's pictures of our house. I was a baby. Of our house, like the front awning broke off. All the little juices that my mom had for me, and I'm old enough to where the juices used to be in glass bottles. That's really sad. But they all came off out of the cabinets and they were shattered all over the floor. The house broke. Yeah, it was really intense, and it was like close to my birthday in October. So my mom said like nobody wanted to come to my birthday party because they were scared of Whittier. That was a huge earthquake. So I don't remember that, but I did live through it. And then you have the Northridge earthquake, which I remember my dad woke us up in the middle of the night. He like ran with us on his back and he threw us under the table in the living room. That was traumatic. And so now, like recently this year, there was an earthquake in the middle of the night here in Whittier, in Uptown. And I get so freaked out that I think I'm traumatized, and my husband like makes so much fun of me because like I'm shaking and it's scary shit. I don't know why I get so scared. Maybe you guys, younger people, you spring chickens, little whippersnappers, maybe you guys aren't that afraid, but if you've survived them at a young age, you're very traumatized. Yeah, so that's my little story about my traumatic events that I can talk about with you guys. All right, so let's keep going because the more I talk about this, the more freaked out I get. I also took a class in my undergrad. It was a natural disasters class, and it was an elective because I was an environmental science, and all they did was talk about like scary crap, like volcanoes, earthquakes, tsunamis, and they talked about how to survive and where to go, and if you're in a earthquake, and every time you go somewhere you should look for exit routes, whatever. So if you have anxiety, do not take that class, because I think for a good year I was so freaked out in public. I didn't want to go anywhere, so I don't know. All right, moving on, let's talk about volcanism a little bit. And remember, this would be more of a geology class. So it's very important to talk about it in a physical geography class. It's the brux of it, right? It like really is how we get all our physical features here on Earth, our mountains, our earthquakes, our volcanoes, trenches, all that stuff, right? But it is also geology, so they're very interrelated. If you're interested in this, major in geology, but you would be learning more about minerals and contents of soil, all those different things. So it just depends like what you really like. Volcanism is a term that refers to all the phenomena connected with the origin and movement of molten rock. This includes the well-known explosive volcanic eruptions and much more quiet events. When magma is expelled on the Earth's surface while still molten, activity is extrusive and called volcanism. I have a little joke for you guys. What did the baby volcano say to the mom volcano? I lava you. Ba-dum-bum. So maybe that'll be on the quiz to see if you guys are paying attention to this lecture. Let's look at volcanic distribution. Areas of volcanism are widespread all over the world, but their distribution is uneven. It is associated with plate boundaries. However, you can find volcanoes in the middle of a continent, so it doesn't have to necessarily be like along an oceanic trench, as we saw, right? It could be pretty much all over the world. Volcanic activity is primarily associated, yes, with plate boundaries. The most notable area of volcanism around the world is around the margin of the Pacific Ocean, which we call the Pacific Ring of Fire. Locations of volcanic activity on the interior of plates are called hotspots. So hotspots is usually where magma rises along the margin of plate. Magma usually rises along the margin of plates, as we saw, right? But there are places on Earth where magma from the mantle comes up to the surface where there is no boundary. These are hotspots, rising magma plumes of heated material rising through the mantle. As magma rises through the plates above it, it creates a hot spot and or hydrothermal features on the surface. The most dramatic hotspot activity is the Hawaiian Islands. So you have this oceanic plate, right? And you have magma rising continuously up. As it rises, it creates a little island, but the plate is moving this way. Does that make sense? So this island moves away, and then a new island is formed, a new island is formed, a new island is formed. So this is why you have this chain of islands, beautiful islands, in Hawaii, because this is a hot spot location. The Pacific Ring of Fire, you have a high number of earthquakes and active volcanoes along the rim of the Pacific Ocean basin. So this is all where you have a high number of earthquakes and volcanic activity. And so you have the Aleutian Trench here, you have another trench over here, lots of volcanic activity, lots of islands that are formed along here, lots of seismic activity as well. Here you go again. Here's the other trenches. Here's where you have volcanoes are those tiny little triangles. You have the Aleutian Trench up here, Japan Trench, Mariana Trench, Middle America Trench. I mean, this is where you have many subduction zones. And along those subduction zones, you're going to have volcanic arcs, right? Mount St. Helens, Volcan Popocatépetl, where my dad is from, Mexico City, DF. We were supposed to actually go there this year, but again, just like with everything, that was a no. Mount St. Helens, this was a recent volcanic eruption in the United States that killed actually 13 people. Volcanic activity. So at any time, there could be around 550 active volcanoes in the world. On average, 15 of them will erupt this week, 55 this year, about 160 this decade. In addition to surface eruptions, there's also a lot of underwater volcanic activity. Some volcanoes may have an active life of only a few years, whereas others are active for thousands of years. Volcanoes provide vital services to the planet, elements for planet's growth, and it is still theorized that water on Earth today was originally released as water vapor during volcanic eruptions during the early history of our planet. So either, God made the oceans and the skies, on the seventh day he rested, right? If you believe in creation, that's a theory. How can I say this? I'm not here to say that that is not true. Maybe I should re-record this. Anyways, you guys know what I'm trying to say, right? I'm just not trying to get myself in hot water here. But that is a theory. The Big Bang Theory, creationism, this is all theories because we do not know. There you go. Lava types. So you have magma versus lava. What's the difference? Magma is molten mineral material below the Earth's surface. Once magma hits Earth's surface, then we call it lava. Ejection of lava into the open air can be volatile and explosive, or it can be gentle and quiet. So it really depends on the type of lava and the silica content of the lava. So some lava has higher silica, some has lower silica, and that's going to give you either very runny lava, that's going to be more of a gentle kind of explosion or eruption. If it's going to be a very thick lava, that's going to cause explosive because there's like more pressure kind of, right? So it just really depends on the lava type. So you have thicker lava, higher silica. These are felsic magmas, thicker, cooler, higher silica, slow moving lava. These are explosive eruptions. Then you have mafic magmas, which are hotter, more fluid, run faster. They're quiet and gentle. So like think about like the way honey flows versus the way, I don't know, peanut butter flows. If you get like that organic creamy peanut butter, it'll still flow, right? It's just some flows faster than others, if that makes sense. Pyroclastic flows. These are high-speed avalanches of hot gas, ash, and rock pieces called pyroclastic flows. These can go up to 100 miles per hour, and the ash is hot enough to kill you. I mean, let alone the lava that is coming afterwards. The collapse of a lava dome or rapid subsidence of an eruption column during an explosive eruption can lead to terrifying high-speed avalanches of searing gas, ash, rock pieces called pyroclastic flows. The very famous 1902 explosion of Mount Pelee in the Caribbean destroyed the town, killed thousands, 28,000 inhabitants. You also have Mount Pompeii, where you had those people kind of like, almost like set in stone, if you will, because of those pyroclastic flows. Different types of volcanic peaks. So you have a shield volcano. They're built up of layer upon layer of solidified lava with little pyroclastic material. They're never steep-sided. I actually went to Hawaii when I was like 17 and we hiked this. And you know when you're 16, 17, like you're a brat with your family? Well, I was that brat. And they were like, oh, let's go hike the volcano. I was like, I don't want to. And we ended up doing it, and it was like the best experience of my life. And if I were a little bit older, I think I would have enjoyed it more. I don't know why I was like a brat during that day. Anyways, coulda, woulda, shoulda, huh? Composite volcanoes. These emit higher silica lavas. These erupt explosively. I'm sorry, guys. They develop symmetrical, steep-sided sides. Mountains build up steep sides by having layers of ejected pyroclastic ash and cinders. Most famous examples are Mount Fuji, Mount Rainier, El Volcano Popocatépetl. So these are like the iconic volcano, right? Maybe when you did your little project in school, you did a composite volcano with the, what is it, vinegar and baking soda eruption? I don't know, I never did that. Here's El Volcán Popocatépetl, very close to Mexico City. It's about 40 kilometers south of one of the most populated cities on earth. And I mean, it's always smoking and erupting. My dad calls home sometimes to where he grew up and they're like, oh, El Popo está fumando, meaning that, you know, El Popo, which they call El Popo, short for Popocatépetl, is smoking. So I think that's pretty interesting. I wanted to hike it when we went, if it wasn't erupting. Lava domes. So lava domes are also known as plug domes. They have masses of very viscous lava that are too thick and pasty to flow far. Lava bulges up from the vent, and then the dome grows largely. Monocraters are a chain of young plug domes just to the east of the Sierra Nevadas and the Yosemite National Park in California. Cinder cones, this is one in California. I actually hiked this one. So you go up through here and you're able to go into one when I went on a field trip with my undergrad class. This is a caldera. They're uncommon in occurrence, but they're very beautiful. They're produced when a volcano explodes and it like implodes or collapses on itself. And it's resulting in this immense basin. And once it has an inflow of water, then it's a great area for a lake. This is Oregon's Crater Lake. And then supervolcanoes. So we do have one here in the United States. It is a term used to describe a volcano that can release 1,000 cubic kilometers of magma. And if that doesn't mean anything to you, it has like more magma than the 5 Great Lakes or something like that. So it's rising up from a hotspot. Yellowstone is a hotspot, and that's why you have such diversity and geological dynamic. It's so dynamic in Yellowstone because of the supervolcano. You have thousands of tremors a year. You have this underground giant cauldron of magma. You know, the last eruption was 640,000 years ago. There's no way to say if it will explode again or not, or how soon it will, but because of this dynamic and extreme environment, it makes Yellowstone as unique as it is. You have superheated pools, you have the Grand Prismatic Spring, you have Old Faithful, that famous geyser. So this attracts about 3 million people a year. So it is a reason why Yellowstone is so unique. I haven't gone. I would love to go. So you guys, that's it for today. There's a lot of stuff to watch on your modules. There will be something about these volcanoes. Yeah, so take care of yourself, stay safe, and I will talk to you soon.